So I apologize for the fact that my entire talk is going to be in the middle of your coffee break, so I'll try to move as quickly and effectively as possible. So I'm going to be talking a little bit about high-performance computing at Lawrence Livermore National Lab, and I want to highlight the High-Performance Computing Innovation Center, which is an outreach activity that's a new outreach activity put forward by Livermore, which I'm leading there. So let's talk about computing first. So computing really is endemic, I would say, at Lawrence Livermore, especially very large-scale computing. If you look at, let's see, do I have a... So Livermore was dedicated as a laboratory in 1952, in fall of 1952, and actually in spring of 1953, our very first supercomputer was installed, so a mere 6 months later. And that sort of chart has continued as time has gone on. This chart looks a lot like the top 500 list, which I'll show you a little bit later. In fact, many of these computers, which were our premier or signature computers at Livermore, were the #1 or #2 or #3 machine in the world, and that persists to this day. And the reason for this is actually straightforward, and that's because some of the calculations that we do at Livermore, and this is true of all three of the NNSA labs, Sandia and Los Alamos as well, is we have problems we need to solve for which it's either extraordinarily expensive, highly illegal, or grossly immoral to actually do the experiment. And so we're required to actually approach that science with computers, and that's what we do. It's a fairly, it's a square-mile facility of people who are trying to solve problems with these computers. That necessarily focuses us to keep pushing the very limit of what's available on computing. We often buy serial #1 of a computer because we've actually worked with the vendor to build the computer to meet some of the needs that we need inside the laboratory. And then, of course, there's all the requisite expertise that goes along with using those machines. So I thank Bill for starting the discussion of what these machines actually look like. It's really very ugly, right? I mean, so a current modern supercomputer, so here's the #2 in the world and the #3 in the world, the Titan machine at Oak Ridge and the Sequoia machine at Lawrence Livermore. These are behemoths, right? I mean, first of all, they fill entire rooms, not casual. Lots of moving parts, hundreds of thousands of cores, or well over 1 million cores, occupy millions, they require millions of watts in order to execute. These are very complicated machines to use. And I think that's one of the points, there are a handful of key points that I want to make sure I get across. And that should go without saying, but I think it's really important because of the point that was made earlier, that Philippe made, that an exascale computer, which is what we're trying to reach toward, is going to mean that petaflop computing is available routinely. It's going to be available at a desktop. But it's not going to look any better. It's not going to be a petaflop in your laptop, or rather, I mean, it might be, but it'll be a petaflop that looks like this, right? This is what 20 petaflops looks like. It's like 1 million moving objects. So programming now, everyone needs to be able to learn how to parallel program if they're going to be able to use a petaflop on their desktop. This can't be just the purview of the rich and famous. And this is sort of what it is right now. So if you look at the whole community of people who are doing high-performance computing work in this country, or I would just say computational research in this country, not just high-performance computing, you wind up with the people who are working in the petascales right now. And like I said, this is this has million or so moving parts that you need to contend with. But this is happening basically at the national labs. I mean, there aren't very many places that have computers at that scale right now. The great swath of work going on at the subscale is happening, at the terrace scale. It's thousands to hundreds of thousands of moving objects. And so there are students at places like Stanford or Harvard or RPI where they have access to computers where they're starting to really learn how to do parallel programming at that scale. But that's actually still the very elite. The great majority of people who consider themselves to be doing scientific or research-oriented work on computers are still working at gigascale, and this is basically desktop level, 1 to 100 CPUs, and they're not really thinking about parallel programming as an ordeal. It's just something, you mess with it a little bit. Whereas, those of us who have to work up here realize that this gap is huge. I mean, moving a code that can scale from a dozen nodes or a couple hundred cores to something that actually scales to 1.5 million cores, that's not something, we don't have the tools to do that. So I appreciate Bill's comment about everyone staying in their lanes. Everyone does their jobs, right? You have the tools, you have the parallel programmers, and you have the architecture. Well, we're doing the sports equivalent of winning ugly right now. So the offense isn't scoring, then the defense has to, and so you wind up playing outside your role. That's not ideal. That's very inefficient. But we're winning ugly right now. We can't continue to do that. We really need to effectively utilize the entire community as we go forward to Exascale. And that necessarily means that the lessons we learn when we do these bleeding edge simulations, you saw some just a moment ago from Ramesh, you saw some from Jackie earlier. I'm going to show you some now as well. These lessons have to filter down to the people working at the next levels so that they learn some of those skills, and those filter down to the people at the next level, because when this looks like Exascale, then you add another 0 to all of these numbers, and that's just going to continue to happen. And what we can't afford, I think, is for this tip of the pyramid to simply disconnect, and so you wind up with this being 1 billion or 10 billion, and this is still at 1,000, because now there's a communication gap that has to be overcome. So Livermore is one of the things we're doing to try to address this is the Innovation Center, which I'm going to talk about. And in order to make that happen, we have to broaden our ability to collaborate outside. Lawrence Livermore is a weapons laboratory, so you can't casually visit Lawrence Livermore. There's a lot, for those of you who have visited, know that there's a badging process, and there's a lot of guards, and there are guns and gates, and it's you don't casually visit. So how do we change that? So in a project that we're doing jointly with Sandia National Lab, it's in Sandia, California, across the street, we're building what we call the Livermore Valley Open Campus. So here's a view of that area. This part here is Livermore, this is Sandia, and this is actually a public road, so that's not part of the laboratory. We're trying to create an area on the side which is going to be outside our security perimeter, which enables more casual collaboration with industry and with academics. Doesn't have some of the restrictions. So just a quick look, I don't want to spend a lot of time on this. So here's again this view of the facility. This is roughly a square mile. And we have a little piece that we've already done, and so has Sandia, that we've actually moved our gates, moved our fences, so that there's a little bit of the lab which is outside the fence. And that's in fact where my office sits. I sit here. So actually, if you were to visit me as opposed to the rest of Livermore, you could simply drive down Greenville Avenue and pull into my parking lot. And there are very few people at the laboratory who can say that. And Sandia has done the same thing. There's a spot of their laboratory, and they put their combustion research facility outside the fence. So you can visit them. We have some plans to actually build larger buildings and build an entire campus out of this. Eventually, this is going to be something that has industrial partners inside, that has academic partners inside, and it's just a research campus that's beside the national laboratories. So the Innovation Center, which is the project that I lead at Livermore, really talks about taking two things and making them available. And that is supercomputing and the expertise to use that supercomputing. Because as I just pointed out, those things have to go together. The computing itself, I could give you an account on one of those machines, and if you can't program 1 million cores, then you're going to wind up working at a fraction of the efficiency you would have had if you just used your laptop, which was a heck of a lot easier to use. So we make available, whoa, I didn't want to do that yet. We make available 5 petaflops of a Blue Gene Q machine, which is currently the #9 machine on Earth, the Vulcan computer. We have other machines that are available as well, but that's sort of the signature machine. We also have a 300 terabyte Intel cluster called Catalyst. This is a very different machine. It's several hundred teraflops, but it's not a calculation engine. This is a big data engine. It has a ridiculous amount of memory and a very high bandwidth, and we're exploring data utilization for that. And of course, access to teams of people who know how to use this. So let's talk about partnering with industry. I mean, I'm glad that Philippe was here and talked a little bit about the industrial use of some of these computers. Industry tends to lag behind where we are at the national laboratories. They also have problems that they're solving with computers, but they don't buy serial number 1. They tend to buy a little bit later. And in fact, historically, they've been about 5 years behind. So here's a chart of the number 1 machine on Earth, the top 500 list, and here's the #1 machine that's in U.S. industry. And you can see that where we currently sit is about a 5-year gap. What that really means, I mean, you have to think of this in terms of time travel, right? Because that means the top industry machine in the US is solving problems at the limit of their machine that we were solving 5 years ago at the labs. Or conversely, we're solving problems on our computers now that they won't be able to solve for another 5 years. And 5 years is a long time in industry. But that's the very #1 machine. a shocking number of industrial calculations are still being done, I would say, at the desktop level. And I can say that, you know, now that I actually work outside the laboratory to some extent, and I talk to industry partners, I'm shocked at the number of times that I say, well, how are you doing that? No, we have an Excel spreadsheet for that. It's like, really? You're doing $1 billion business on your Excel spreadsheet? That's what you can do? It's crazy. That's a 15-year gap. 15 years. 15 years is a lifetime in industry. That's an eternity. And yet that's the gap we're facing in terms of computing. You don't want to operate here. You want to operate up here. That's a factor of 100,000. 100,000 is where we're operating versus what desktop computing looks like. And that's an enormous amount of computing power. It's not speed, though. And that's, I think, one of the things, and people talk about the fastest computer. They often say the top 500 list is a list of the fastest computers. Well, I guess technically that's true, but it really is the most complicated computers. What you really do with that factor of 100,000 is a factor of 100,000 more realistic a simulation, a factor of 100,000 more complicated a simulation, not necessarily a factor of 100,000 faster simulation. So I'll give you an example. So let me go backwards in time a little bit. So circa 1986, this is what a car crash simulation looked like. That's what they were just starting with. That was the extent of what they could mesh. That was the extent of what they could figure out. This is sort of what current car crash, a few years ago now, car crash simulations look like. And you see, you're not just looking at, a countable, like by hand number of mesh points on just the frame. You're actually talking about the entire, you have the rubber, the rim, you have all the fender, you have all the metal sheeting. All of that is being modeled because it all gets coupled together. That's a factor of 100,000 more complicated than that. We, however, at the labs are a factor of 100,000 more than that, because this is desktop computing. This is being done on laptops right now. So what can you do if you have another factor of 100,000? Well, now you can do some things that are truly spectacular. So I'm going to give you one example, just in the interest of time. I'm happy to talk about more, but I just want to give you a flavor of where you can go. So an example of what we did inside the Innovation Center is working with our partners at IBM. We developed a whole heart model that's going to look at the electrophysiology of a beating heart. And we're going to do that at near cellular resolution in real time. And that winds up being game-changing. And that's actually the second point that I really want to make sure that I make and I want everyone to walk away with. Factor of 100,000 is huge. It's game-changing. It's not a matter of doing whatever you were doing. And someone mentioned earlier, Exascale is not going to be about doing the same thing a little better. Well, I completely agree with that. Exascale is about doing something completely different. It's seeing different science that you didn't see before. It's getting understanding that was impossible before. And this kind of calculation, I hopefully will make the point for you. So sudden cardiac arrest is a leading cause of death, so it's a useful thing to study. We want to be able to look at an arrhythmia developing inside a heart. So we're not going to look at the mechanical beating. This is all talking about the electric circuitry of the heart, which is how your heart actually beats. So we're going to work with our partners at IBM and develop a code that we're calling Cardioid, which is going to leverage this resource that we have at the laboratory. And how does that happen? Well, first we needed a model of a heart, and typical researchers working in this space actually just make up a heart. I mean, they know roughly what the geometry is and they make one up. We want to do something a little more accurate than that because we're going to have very high resolution. So we picked a real heart. We used the data set that's available in the University of Florida called the Visible Human Data Set. They have very fine section data of donated bodies that are available for research use. And so we extracted from those images a heart at the highest resolution that we could and then gridded it up. Something like 300 to 700 million cells, depending what we're doing. And then, of course, you have to take that and distribute it on 96 racks of Blue Gene Q. And as was mentioned earlier, that was done by hand. There aren't tools that do that, so you sort of have to know the architecture, you know the problem you're trying to solve, and you set the whole problem up in order to effectively make use of it. You're doing a cell model, so I mean, without going into all the biology, the beating of a human heart is actually a pretty remarkable thing, right? I mean, there are a number of ion currents that potassium and sodium and calcium that have to be monitored. They're controlled by channels that act like gate functions, and those gates are themselves concentration-dependent responses. And so you're doing this coupled set of a reaction-diffusion equation. And it's all beautiful. You can all express it mathematically, and people have done this. There are published models for this that are pretty well understood. You're going to do that this is an interesting problem because you're going to take 700 million cells, let's say, at our highest resolution, and put it on 1.6 million cores. That means you're really talking only a few hundred cells per core. So this is a fun computational problem because you're going to try to scale a set of equations across the entire machine. So it's sort of a weak scaling problem at the resolution you're doing. But it's also a strong scaling problem because you're not actually doing a whole lot of work per core at the end of the day if you want to make it happen in real time. So this code that we eventually developed does both. It's actually both a strong and a weak scaling code, and that was sort of cool. So this code was written from scratch. There are existing codes you can go out and that solve these equations because the equations are well known, but they weren't amenable to the scaling that we needed. So we wound up coding it completely from scratch. Winds up being 3 orders of magnitude faster than the nearest work that has ever been published in this, and this was a finalist actually for a Gordon Bell a year ago. So what does it look like when all is said and done? So I'm going to show you a couple simulations. This one is a wedge of a heart, and we can in fact do a whole heart, and I'll show you that in a moment. But we did a wedge here because we're comparing directly to an experimental paper that was published, and they had a wedge preparation of a heart, and we were going to with this particular drug involved, disotalol, which is a textbook drug for causing arrhythmias. So we're not going to invent something here. We wanted to prove that the thing worked. So here's a wedge of a heart with you have endothelial cells, epithelial cells, and they're mid-myocardium cells, which you can't see at the moment inside the heart. Each of these have different responses as the voltages change. So your heart sits at rest actually at a small negative potential, and that's represented by blue here. As your heart beats, it actually goes to a slightly positive potential and then all comes back down again, and that's what all the ion currents do, is make all that happen. So you're watching here a heart in between a beat. We're going to stimulate the heart. The stimulation is going to come in from the side, and you're going to watch as the heartbeat goes through. So here we go. Here's the stimulation. It goes through. The whole heart turns positive, starts to turn negative again, and I wanted to stop that. Okay. So and now I'm going to put a second stimulus in, and this is actually one of the causes of a heart attack. If you get a stimulus in your heart at the wrong time. I mean, if all of you are familiar with an ECG, you sort of have the big beat, and then there's a little beat that goes the wrong way, and then nothing happens for a while. Well, that nothing happens for a while is sort of important as your heart rests back to its negative potential. You don't want to have a beat start to happen at the wrong time, because then it can get confused. That's sort of what an arrhythmia starts to look like. So here you're watching these areas that haven't quite repolarized. Those are these mid-myocardium cells. They're known to delay a little bit in the repolarization, and everyone has them. I mean, this is just a function of your heart. This is usually not a big deal unless you happen to have a drug like disotalol in your system, which actually blocks the potassium channel on one of the gates. And so the effect of that is that it makes it very susceptible to a secondary stimulus, and that's what you're about to see here. So here the wedge with the drug can't escape the second stimulus, whereas a normal heart would take that insult and sort of and heal past it. It would go back to its rest. So what you just saw there is the beginning of what they call a transmural reentrant pattern. Transmural because it goes from the wall and goes inside, as opposed to less fatal forms of arrhythmias which involve scrolling on the outside of the heart. That doesn't actually involve the heart beating as much. So turns out that's not quite enough. In order to talk to doctors about that, because they don't have information of what happens at every cell of your heart at every moment in time with all the currents like we do, they want to know what the ECGs look like. So we had to do a separate project on top of that in order to create an artificial body around our artificial heart, and then put artificial leads on that artificial body in order to actually measure what the ECG of our beating heart looks like, because then we can compare that to doctors. And that's a whole fun story in itself, but needless to say, we did that. And so I want to leave you with looking at an arrhythmia developing in an entire heart, looking now at from the top and from the side. And this is why this is fatal. This transmural pattern wraps inside the heart and back in several axes, and there are vortices involved here, and that disrupts the actual flow of blood. So this means your heart does this very rapidly. This whole thing was only 2 seconds. So I'll show you what it looks like in sort of real time. So here's a simulation happening over 40 seconds. And I remind you, we can do this in real time. So prior to this, one beat would have taken a half a day on the best simulation that was done before, which is why people didn't do these kind of studies. This would have been like a multi-year study just to do the one calculation. We do that in real time. That's game changing. That's what a factor of 100,000 buys you. Here you can compare what we see as the arrhythmia that developed in our artificial heart with the arrhythmia of an actual patient. And again, one of the reasons it's game-changing is because you can actually learn things that you couldn't have learned before. It turns out that one of the difficulties with understanding arrhythmia was there was no well-accepted explanation for what this modulation means. So the arrhythmia is the fact that it's all happening very, very rapidly and your heart's not beating in a functioning manner here. But that modulation was witnessed but not understood. And we see exactly the same thing in our simulation, and we can now explain that. So that's now a medical result that came out of a computer simulation. So anyway, I'm just going to end with that and say that, you know, I've showed you one example out of biomedicine. Factors of 100,000 matter. They matter a lot, and they can affect pretty much every space we have. Thank you.